Okay, hello everyone. Now we are going to solve example 2.5, which is in fact the example of type 3 problem, where we are going to find the unknown diameter. Now it says we have a galvanized iron pipe with a roughness height of 5 times 10 to the minus 2 millimeters. The length of the pipe is given as 100 meters. It is under the head loss of 10 meters, and discharge of 3 liters per second is being carried in that pipeline. And the question is, for these given conditions, what is the required pipe diameter? So what we do, we list all the variables, and we see that we are asked to calculate the pipe diameter. Since HF should be in meters, we forgot to write that meters there. And discharge is converted to cubic meters per second. Kinematic viscosity of water is used. Epsilon is given. And if you remember, for type 3 problems where we are trying to solve for the diameter, in order to find the friction factor F, which is function of Reynolds and relative roughness, if you look at those terms, Reynolds is nothing but average velocity times d divided by kinematic viscosity. So you are in need of that diameter of the pipeline to calculate Reynolds number. And the other term is epsilon over d ratio. In fact, in type 2 problems, we calculated epsilon over d, and at the very beginning we said, okay, I'm going to assume hydraulically rough flow. Hence, with that epsilon over d only, we calculated the corresponding F. But here, as diameter is unknown, we not only can calculate Reynolds, but also epsilon over d ratio. So I don't have anything in hand to find that F value. So what we do is, as we had discussed previously, we assume one F out of blue. So what we had said is, if you just look at the range of that F that we have in that Moody's chart, we try to be somewhere in the middle. So we start with the iterations with F to be equal to 0.02. Now, if you look at the procedure, as we know, velocity is nothing but Q divided by A. A is pi d squared divided by 4. HF, using Darcy-Weisbach equation, FL over dv squared 2g. In terms of this V, I can substitute this 4Q divided by pi d squared. And, sorry, I can obtain the relation of HF to be equal to this. So, d to the 5 is the exponent for the diameter. So I'm going to solve for d from this equation, which will be equal to F times 8L Q squared divided by G pi squared HF to the power 1 over 5. Now, if you look at this relation, I know the length, I know the discharge, G is gravitational acceleration, HF is the friction loss that is given. So I know every term here other than F. So what we do is we calculate those numerical, we put those numerical values to write D as a coefficient times F to the power 1 over 5. And if you do calculate that coefficient for this example problem, it becomes 0.0942 times F to the power 1 over 5. So what I need to do is, after each assumed or calculated F, I will just substitute in that D relation to solve for the diameter value. Similarly, Reynolds is calculated as V times D divided by kinematic viscosity. And after you find your D, you can solve for your velocity and then calculate that Reynolds number. Or at the very beginning, you can write your Reynolds number. Here, in terms of V, you can write it as 4Q divided by pi d squared. Hence, your Reynolds number will end up with 4 times the discharge divided by pi d kinematic viscosity. So it is up to you. If you do not want to recalculate velocity at every step, you can directly get rid of that velocity simply by writing it as Q over A at the very beginning. And if you do so, the Reynolds equation becomes 3819.7 divided by the diameter from the relation of Reynolds in terms of diameter only. And for epsilon over D ratio, epsilon is already given. Do not forget to convert it to meters, because from the solution procedure, we are going to obtain diameter in meters. So it is a very common mistake. Please be careful. So write your epsilon over D ratio as 5 times 10 to the minus 5 divided by the diameter that we have. And then we know that Swami-Jain relation for F, which we are going to use in Darcy-Weisbach equation. So we said, again, we are going to prepare a table. It is really very, very helpful for us. So initial F, this is F assumed only for the first iteration. So if you assume 0.02 for the initial F value, just substitute that F into that B to be equal to the constant times F to the power 1 over 5 relation. And if you do so, your diameter will become 0.043. Use this to calculate velocity in meters per second. With the velocity, you can calculate the Reynolds number. From the D, you can also calculate epsilon over D ratio. And with the calculated Reynolds and epsilon over D ratio, you can calculate the friction factor from Swami-Jain. So as you see, they are not equal to each other. So I'm going to make a continued iteration. So I take it there. With this F, find nu D. With nu D, calculate velocity. Then solve for Reynolds number. Then calculate epsilon over D ratio. You know Reynolds, you know epsilon over D, so solve for your F. As you see, they're equal to each other. And that means we can stop. If you stop at this point, you see that your diameter is 0.044 meters. So it is like 4.4 centimeters. Well, most probably we are not going to have 4.4 centimeters pipe that is commercially available. So if you were given a list of diameters for commercially available pipes, all you need to do is to choose the next larger pipe size which is commercially available. So if you were to have 4 and 5 centimeters of diameters, then you have to select D to be equal to 5 centimeters. So whatever that commercially available pipe size is, you will use the next larger pipe size that is commercially available. I hope it is clear.